So welcome back, learners. This is another part of our revision for kcse. Now, this question appears in Form 3 and it mostly talks about Gay-Lussac's law. So if you're watching our channel for the first time, kindly take time, subscribe, like and share. In this particular question, you're told 12 grams of methane and 12 cubic centimeters of methane and 48 cubic centimeters of oxygen were exploded together. The final volume measured under conditions was 36 cubic centimeters, neglecting water formed. 24 cubic centimeters of this was unused oxygen. Show the ratio of the reacting volumes of gases referred to and the gaseous product formed. Now from the question, you've already been told that for methane, it is 12 cubic centimeters. Now I've already written this equation here. I have to check whether this equation is balanced first and foremost. Now carbon here is 1, carbon here is 1. Hydrogen is 4, so I must make hydrogen on this side also be 4. How do I make hydrogen on this side 4? By writing there 2. So if I write there 2, then the hydrogens are balanced. But oxygen on this side are now 4. So I must also write here 2. Must also write at this point 2 to ensure that the number of oxygens are also balanced. Now, for methane, we've been given the volume of methane. So I'll come and write it here. The volume of our methane is 12 centimeters cubic. 12 centimeters cubic. And the volume of oxygen initially was 48. But unaambiwa, you know this oxygen is the one that was being used. At the end of the experiment, the volume of, you are told 24 of this was unused oxygen. That means at the end of the experiment, the volume of oxygen remained as 24. Inamaanisha 24 ndio ilitumika. So ikabaki 24. Initially ilikuwa 48. But you've been told that the final volume that you formed is 36 cubic centimeters, neglecting the water formed. That means water is not counted in this experiment. So this water has no volume in this particular experiment. Hii haina volume kwa hii experiment. So the volume that we have here is the volume of this carbon 4 oxide, which in this case is going to be 36. Now once you do that, but this is 36 cubic centimeters. Once you do that, then you look for these gases. Which one has the lowest volume? It is methane. So because methane has the lowest volume, what you simply do in this particular case, you divide here by 12, here also by 12, here also by 12. So here you divide by 12, here you also divide by 12, and here you also divide by 12. So if you divide that, you're going to get your ratio here is going to be 1 to ratio. If you divide this is 2 to ratio, this is ratio 3. So your ratio is going to be ratio 1, ratio 2 to ratio 3. That is the ratio of methane to ratio of oxygen and to ratio of carbon 4 oxide. So I hope you have understood that concept, learners. I want also to do another question that is still on mole concept. This is going to form the third part of our question on mole concept. Now this question down here, you're told 4.9 grams of adiabatic acid was dissolved in water and the solution made up to 500 cubic centimeters. If the concentration of the hydrogen ion was 0.3 molar, calculate the relative molecular mass of the acid. Now I want you to look here very well. If you're told to calculate the relative molecular mass of the acid, you know, at triabasic acid, nilisema hydrogen ni 3. That's when nimeandika hapa 3, H3X. If you dissolve it in water, you get 3 molecules of hydrogen ions plus X. But you've been told here that this 4.9 grams was dissolved up to 500. That is very important for triabasic acid. So the main reason you've been given this information here is because this information is going to help you to get grams per liter. Grams per liter. Now we've also been given the concentration of hydrogen ions, which are these ones. So we have the concentration of hydrogen ions. Umeprovide na swali. What is the concentration of hydrogen ions? 0.3 molar. And then you've been provided with the grams of the diabasic acid that was used in this particular experiment. And I want you to be very keen here. The grams of the diabasic acid that was used in this particular experiment was 4.9 grams. And these 4.9 grams, these 4.9 grams, they were dissolved in what volume? 500. This one was in what volume? It was in 500 cubic centimeters. Now, if 4.9 grams is in 500 cubic centimeters, if you want to get grams per liter, remember a liter is 1,000 cubic centimeters. So just simply come here and say, what about 1,000 centimeters cubic? Okay. So if you cross multiply this, so that now you are going to get something which is called grams per liter. You're going to get your grams per liter, and if you solve this very well, learners, you're going to realize that as you solve this, you'll realize that your answer in this particular case is going to be 9.8 grams per liter. Okay, so we have our grams per liter. And remember, we want to calculate the relative molecular mass of this diabasic acid. Remember, this is grams per liter of the diabasic acid. Grams per liter of the diabasic acid. Okay. Now, we only have the moles of the hydrogen ions, the concentration of the hydrogen, which is 0.3. But remember, if you look at the diabasic acid, which is H3X, if you look at the concentration of the diabasic acid, which is H3X, to the hydrogen ions, these ones, to these hydrogen ions, I want to look at that mole ratio. Here there is nothing, but here there is 3. So that means our mole ratio is ratio 3 to ratio 1. So that means, because we have the moles of the hydrogen ions as 0.3, then we can also get the concentration of this diabasic acid. We simply, because this is 1, I mean this is 3. Let me change this. This is ratio 1 to ratio 3. Ratio 1 to ratio 1. Let me change this. This is ratio 1 to ratio 3. And I want you to understand why I'm saying ratio 1 to ratio 3, because if you look here very well, I want to look at this very well, you're going to realize that at this point, diabasic acid, huku hakuna kitu, so hapa ni 1. Lakini hapa kwa hydrogen, hapa ni, this is supposed to be 3. So that means this diabasic acid yenye ni 3 ndio 0.3 molar hii tumeambiwa, because this is a concentration of hydrogen ions which is 0.3 molar. So if the concentration of hydrogen ions is 0.3 molar, then it means the concentration of diabasic acid simply divided by 3 will be 0.1 molar, or moles, because that is still moles per liter. Okay. Now, because we now have the moles of the diabasic acid and we have the grams per liter, remember this is concentration, so this has to be molar. Because we now have the concentration of the diabasic acid and the grams per liter of the diabasic acid, it means we can get the RFM, or the relative molecular mass of the diabasic acid. We simply relate these ones, these two. And we are going to apply that formula that I told you. I told you, for us, we usually say concentration or molarity is equals to grams per liter is equals to grams per liter over the RFM. So that means, in this case, we want the RFM, which is the relative molecular mass. So what you simply do, you simply cross multiply these two. Now, cross multiply hapa, utapata in order for you to get the RFM, your RFM will be equal to your grams per liter, over your molarity of the concentration, over the molarity, which is also the concentration. So in that manner, you will be able to get the RFM. So in this case, our RFM is going to be equal to our grams per liter, which is 9.8, and then we divide it by our molarity, which is 0.1. You divide it by a molarity, which is 0.1, and then now from there you're going to get that your relative molecular mass is going to be equal to 98. Your relative molecular mass is going to be equal to 98. So up to there, learners, I hope you are learning something and you've learned something new up to this point. So this now becomes our answer. Thank you so much for watching our channel, and I hope you also share the link with your colleagues from other schools so that they can also subscribe and learn through our channel. Thank you.